Let's get started here. All right, so we're going to take a look at this. We're going to take a look at this FRQ problem. And this is actually given a couple of years ago. And it's just looking at a buffer problem. And it simply says, hey, a student is asked to make a buffer solution of 3.40 by using, in this case, a 0.100 molar of nitrous acid. So that's a weak acid because that's not nitric, it's nitrous acid. And also you got 0.1 molar sodium hydroxide. Explain why the addition, in this case, of the sodium hydroxide to the 0.1 molar nitrous acid can result in the formation of a buffer solution. So for this one, if you look at it, what I'm actually given is I'm given, in this case, 0.100 molar of that thing right there. But of course, because they're going to go in here and they're going to add, in this case, sodium hydroxide to it, I know sodium hydroxide in this case happens to be a strong base. So if I add HNO2 and I add the hydroxide here, then I know what's going to end up happening. It's going to be a neutralization reaction. That's where it's going to go. And what it's going to end up producing in this case is it's going to produce H2O. And also it's going to produce the thing that I need in order to be a buffer solution in this case. So all you would have to say for something like this, and it did say, hey, show the net ionic equation as well that represents the reaction. This is the net ionic equation. Remember, the reason why I'm leaving sodium out is it would be a spectator ion in this case, so it's gone. One other thing to point out, which I have not talked about, but I'll reiterate it as well, when it comes to weak acids, we always show weak acids as still being together. Do not completely dissociate them. Strong acids, yes, separate. Weak acids we keep together. So this will represent, once again, the net equation. And then your justification would be, hey, by adding the hydroxide, it's going to cause a neutralization reaction to occur and produce the conjugate base that we need. And if you look at the actual rubric that we have sitting right here, you're going to notice that, hey, there goes the exact same reaction. It tells you that the sodium hydroxide is going to neutralize, in this case, the nitrous acid, and it produces that conjugate base that I need, because we know for a buffer we need the weak acid and its conjugate base. Hey, 1 point earned for recognizing the mixture is going to produce the weak acid and conjugate base needed for the buffer, and 1 point earned for that correct net ionic equation. This next problem simply says that, hey, and this was like, I think it was like maybe 3 or 4 different parts to this problem that was given this year for the AP exam, and it tells you that, hey, if we have this weak acid again, and its Ka happens to be 4.0 times 10 to the -4, which means its pK happens to be 3.40. Determine the volume in milliliters of the sodium hydroxide that needs to be added to this thing right here in order to get the pH of the buffer solution to be 3.40. Well, if you think about it, they already told me, in this case, that, hey, pH plus pKa plus the log, in this case, I'm just going to write this out, and there's an Hasselbalch equation divided by HNO2. In a sense, what they just told me is they said, hey, I want the pH of the buffer solution to be 3.4. The pKa is 3.4, which means they're telling me they want these two to be equal as far as their concentration. So I just need to make sure that the NO2 minus concentration is going to be equal, in this case, to the HNO2 concentration. As long as those two concentrations are correct and the same, I get this here. So if you look at it, what do I have? I know that in this case, they want me to figure out how many moles of the sodium hydroxide. And I know that whenever I take the sodium hydroxide reacted with the nitrous acid, neutralization reactions occurring here, right there. And we said neutralization reactions said we got to go B, C, A whenever dealing with neutralization reactions. And we know that, hey, I got to figure out how many moles of this substance I'm starting off with. And luckily for me, I got 0.100 liters times this concentration. Once again, for the concentration, I got 0.100 moles, in this case of the HNO2 per 1 liter. That's the concentration, which will give me 0.0, what do we get here? One more 0. Is that right? No, just 1 0. 1 0 0. And that's going to be moles of HNO2. NO2. So watch what's going to happen. This is pretty easy when you look at it. I know that this is 0.0100. I need to figure out, in this case, how many moles of the sodium hydroxide I need. And one thing that I know is that the sodium hydroxide, I want to get it to where it's going to subtract some of this nitric acid away. But as it subtracts, it's going to start to build some of my conjugate base. So if I look at it, I want these two values at the very end down here to sit as being the exact same value. Which means that I know, in this case, the number of moles of the hydroxide I'm going to need in this case. And if I look at it, the only way I can get these two to be the same is to reduce this thing by half. Because if I get it to go down by half in this case, then half will be sitting here and half will be sitting here. If AP ever gives you a problem like this, they always set it up to where it's just going to be half the original value. It's always that way. I never seen them give you any other way, because if they did give you any other way where these were different values, then these two things would be equal, and it just makes it a little bit more tricky in this case. So if I look at it, I'm going to go in here and say, okay, let's see, we got 0.01 divided by 2. That means I need to go in here, in this case, with 0.00500 moles. And of course, when I subtract that now, it's terrible red. When I subtract that, that's minus 0.00500 moles minus 0.00500 moles. And over here, we're going to get, in this case, plus 0.00500 moles. And then what's going to happen is clearly you're going to subtract out and get 0 right there. But over here, I get 0.00500 moles, and I get 0.00500 moles. I'm done. And the reason why I'm done now is I know how many moles of sodium hydroxide I need. And if I know how many moles of sodium hydroxide I need, and if I know what the concentration of the sodium hydroxide happens to be, I just bring those two together and figure out what volume would I need to get me this number of moles. Once again, it's up to you how you want to do it. Me personally, I love dimensional analysis. Other students like to go in and say, well, molarity is equal to moles divided by liters. And they'll go in here and say, hey, this is 0.100 M is equal to 0.00500 moles. And they'll put over X for liters, and they'll solve for liters. That's fine. Me, dimensional analysis all the way. I know this is moles per liters, so I just go in here and say 0.00500 moles. The concentration, well, I want moles to go down here, so that'll be 0.10. Wait, yes. 0 moles per every 1 liter. Moles will cancel out, and if you look at it, when I sum this thing anyways, it's going to end up being X going in here, 0.1 down there, and it'll be this number divided by the 0.1, and that's exactly what I got right here. And then of course, once I plug this into my calculator, I'm going to end up getting, what do we get here? We get 0.005 times 0.1, which is going to end up giving me, in this case, a number such as 5.00 times 10 to the negative 4 liters. And of course, that's really going to divide by, or it's actually, it's liters. But I can leave my answer here, but I would probably convert it to milliliters. But to be truthful, oh, they did say determine in milliliters, so I need to go ahead and convert it to milliliters. And of course, to convert it to milliliters, I'm just going to go ahead and divide this thing. So, fill this right here. For every 1 liter, I got 1,000 milliliters. And now this should give me the answer I'm looking for here. So 5 second E to the negative 4th times 100 or 1,000 tells me I really need 0.50 milliliters. Just want to see one thing really quickly. Oh, I can't believe it. I didn't even say anything to me. I know my number was a little small. It should have been 5 milliliters. And the reason why, but I was still okay. I'm okay here because the setup is the right way of setting it up. The reason why I have a slightly different number here, no, that's okay. I didn't do anything wrong.
Why would it be 5 much? I mean 5 liters.
No, actually it's not, because this is 1, 1, 2, 3. That's a decimal there. That's a decimal. I would get this number here. That's half the value. That's half the value. Just want to make sure. So I should use half. What volume did you say? Should go with 50 mLs. Why did I get off here? Half the value. Just want to see really quickly, because clearly I made it really quick. That's correct. That's correct. That's correct. This is correct. That's the amount that I need in order to subtract away from it. One or two things happen. Either I didn't copy this question down correctly, which is a possibility. I don't think it is. 0.01 divided by 2. That's 0.005. That's correct. That's correct. That's correct. That's correct. We'll take this. Moles times this concentration of sodium hydroxide. Take that. 0.005 divided by 0.1. Oh, and that's what's wrong. Thank goodness. I just made a small little math mistake right here. This should have actually been, when I plugged in my calendar, I knew something was off here. You get 0.0500 kiloliters, which now, when I move the decimal over 1, 2, 3 places, gives me 50.0 milliliters. I was hoping I had to go back and change these numbers, but it was just that little calculation there. I must have divided instead of multiplied. But that does give you 0.0500 liters. And then once again, they asked it in milliliters. So all the thing you had to do is really just go in here. I just tell them that you need half the amount. And keep in mind, even for a problem like this, you didn't have to do all the work that I did here. I just wanted to kind of show you what we need to do. The reason why I technically did not have to do all of this work is because of the fact that we're starting off with the exact same concentration of the strong base, or the hydroxide, as we have the weak acid. Because we have the exact same concentration, all I need is, once again, half the amount of this. Because now when I go with half the amount, which would be 50 mLs, it's going to cause this thing to go 50% through. So long as the two concentrations are going to be the same, which AP is notorious for always doing it, then all you have to realize is I need half the amount of the sodium hydroxide to force this thing to go through half the neutralization reaction. But at the same time, you could go through and do the math. Not needed, but just kind of look at it and realize they're always going to give an exact same concentration. All right, one last problem I'm going to look at here, and that's going to be this problem right here. Oops. If you look at it, basically what they say is we have a second student who makes a buffer solution. And for this buffer solution, they're going to start off in this case with 0.10 moles of the actual conjugate base. And also they start off with a 1.0 molar of the weak acid. And the question they have is which one's going to do a better job of resisting the actual pH? And if you look at it, for the first example that we had, they had in this case something where it was going to end up being, where was it? Make sure that's the first one. We got a 0.1 of that. So even if we look at it, one of the things that I can see here is that we had a point, kind of like a 0.1 molar here, or 0.05, or 0.05 molar here, and a 0.005 molar down here. And the second example, what they're going to end up doing here is they're going to go in and simply say that I got this high concentration of this weak acid, and also I've got a 0.1 molar of this conjugate base. I can tell easily which one's gonna have a better resistance, trying to resist the change to the actual pH of a buffer solution. If you remember, we said the resistance, the thing that's gonna resist the most, is to make sure that you have highest concentration of the weak acid and conjugate base. And the example that we have here, they're not going with a 0.1 molar, they're going with a 1 molar, in this case, of the nitrous acid. Even if we went with the example where they start off with a 0.1 molar, that's still a lot lower in this case. So clearly I can see that because we're going to have a higher concentration of the actual weak acid and conjugate base, then I know for a fact that it's going to be the one that is going to most resist, in this case, the actual change. And that's exactly what it says here. The buffer made by the second student is the most resistant because the concentration of weak acid and conjugate base happens to be the greatest. Even after we go through and once again add some H plus and an OH minus to it, it's just not going to change as much. So, last thing we'll look at, and then we're done here, is this problem here. I just want to kind of show you, if AP ever gave you something like this, how to approach it. And it's a really easy problem to approach. Basically what we got here, it says, hey, a new buffer solution. In this case, we got HNO2, and also we've got its conjugate base here. And they're showing you a picture. And they're asking you in this case, hey, based upon this actual picture, will the actual pH of this buffer solution be 3.40? Remember, they already told you that the pKa for this thing was 4.0. So what I can do here is I can go in and look at this a couple of different ways. So pKa is equal to 3.40. And remember, we said in order for that to take place, the pH, which is equal to the pKa, which is equal to, or plus, the log, in this case of NO2 minus, over the concentration of HNO2 here. We said that if these two things were equal to each other, and only if they're equal to each other, can this be true? So they're asking, is it going to be greater or is it going to be less in this case? You got two ways in which to approach this. One is you're going to look inside this container, and you're going to just go counting in this case. I'm going to look at the nitrous acid and say, how many do I have? I got 1 here, 2 here, 3 here, 4 here, 5 here, 6 here, 7 here, 8 here, and I got 9 there. So I got 9 of these things right here. And then when it comes to the actual nitrite, I'm going to go in and say I've got 1, 2, 3, 4, 5, and if you look at it, I just made a mistake. And that's why I love, like, with these pictures, I might do X's on one, maybe circles or a slash on another, because I see students who will do this, and they'll end up missing the answer. It's just because they didn't count correctly. So I can clearly see that, hey, that's one that I missed here. So I'm going to go back and make sure that I'm okay here. So what I have is I got 1, 2, 3, 4, 5, 6, 7, 8, 9, that's 10. 10 sitting right there. Which means that when I look at the nitrite, the conjugate base, I got 1, 2, 3, 4, 5. I got 5 sitting here. Well, if you look at it, I got two choices here. One is just to kind of look at it and kind of figure out what's going to happen here. If I have more of this down here, so I got more in this case of the weak acid, I got less of this. Is my log going to end up being positive or negative in this case? Ooh, good question. 10 sits down here, 5 sits down there. That means I got 0.5 sitting here. Log is positive or negative? Negative. Which means that if it's negative, that means I'm subtracting from the pK, which means that, hey, the pH has to be less than 3.4. Now, if you want to, you can go in and express it that way. You can also, for me, I like to just say, hey, you know what? We got more of the weak acid than the conjugate base. And of course, if I have more of the weak acid, it's going to end up being more acidic in this case. Or the other way, which they'll show you, is you can literally just substitute the numbers into the actual equation. I can put in here that, hey, you're 10, you're 5, and just treat those as though they're the concentration. And it will absolutely work out. Because if I look at this, I could say that maybe this is really just 10 moles. This, I could say, is 5 moles in this case. They're all within the exact same volume, so I can say the volume is equal to 1 liter, which means that's 10 molar, that's 5 molar. I can say it's 2 liters. It doesn't make a difference. You're still going to get the exact same fraction working out here. And you'll notice that in their solution, they give kind of the explanation way of looking at it, and they also give the substitution into the actual Henderson-Hasselbalch equation, and they do the calculation. It is completely up to you. You can talk about how it's going to cause the log to be a negative, because once again, the numbers are going to subtract away from the pK, therefore causing pH to be less, or literally substitute the numbers into the Henderson-Hasselbalch and be done with it in this case. All right, this is where we're going to stop. One thing to point out is you'll see some other slides in here. These slides you're not responsible for. They're highlighted actually in yellow, or kind of a greenish color, bluish green. This is what your predecessors used to have to do. They have to go through neutralization reactions, and they would have to go through and then use ice equations and all this stuff. You don't have to do it. AP has removed it, got rid of it. But at the same time, in college, they're going to probably ask you to do this sort of stuff. I'm just putting the notes in there so you can kind of look at it when you go to college, and if the professor asks you, it's in there. Kind of explains the exact same way I used to explain a long time ago. All right, so this is where we're going to stop with this part.